So today we're going to talk about radioactive decay and radiation. And what you see in front of you right here is a Geiger counter. We didn't mention this in class, but a Geiger counter is an instrument that's used to measure radiation. And what you have right here is the kind of instrument in. And what happens is that when something with radiation that's giving off radiation is near, it will give off an electrical impulse, and this Geiger counter will start making a sound that says, hey, there's a lot of radiation here, and this meter will obviously rise. So this is used to obviously detect traces of radiation in the environment. And what is radiation? It's simply parts of the atom given off or broken down. And we'll see that radioactive decay is really important in dating the Earth. A very common element that's seen is uranium 238. So again, if I set a big hunk of uranium 238 in front of this Geiger counter, it would go crazy because that uranium would be giving off different parts of the atoms. It would be breaking down. So we use this in carbon dating and dating the Earth. So it's really important in a lot of different aspects of science, whether chemistry or biology, paleontology, that sort of thing. Okay, so let's start talking about how radiation works. And really, to get to the truth of how radiation works, we need to look at the nucleus of a cell. So this is nuclear chemistry. We're really not messing with electrons much with this. We're concerned about protons and neutrons. So what do we know about protons and neutrons in the nucleus? We know most of the mass is in the nucleus, and protons and neutrons. We know protons, these guys, if I can get my charges right, are positive charges right there and over here. And over here, pretty good pluses there. And neutrons have a neutral charge. So when we're thinking about what happens with the electricity of them, we know that these positive charges are doing their darndest to get away from each other, right? Like charges repel. So you probably are asking, how does the nucleus stay together? Well, neutrons are really, really important. They're in essence the glue that holds an atom's nucleus together. So look over here to the periodic table. We can start with neon and look. Neon's right here on the periodic table. So starting low, we see that the number of protons and neutrons are about the same in an atom. So number of protons is very close to the number of neutrons. Calcium even, 20 protons, 20 neutrons. But what happens when we start getting a larger number of protons, 50 protons? Well, again, think back to this situation right here. If I have 50 protons in there, I have 50 protons that are desperately trying to get away from each other. So I need a lot more neutrons to kind of act as a glue to hold this nucleus together so it doesn't become unstable and start decaying or ripping apart. And you see uranium, 92 protons. Look how many neutrons, 146. And what we call this the strong nuclear force. So the strong nuclear force is what holds this nucleus together, and it's this principle we've seen right here in all of these, that we need a certain ratio of protons to neutrons for that nucleus to hold together, and that's really important. The strong nuclear force is stronger than these electrical forces that are trying to repel these protons apart, thus rip the nucleus apart. Okay, so moving on, we can graph this. We talked about this in class a little bit. We call this the band of stability, and it's pretty simple to look at here. Let's get blue. So on my x-axis, we have, it's a little fuzzy here, but we have number of protons. So 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then on this side, it's blurry, but this would be number of neutrons. So what this band tells me is if there was a 1-to-1 ratio of protons to neutrons, meaning if protons were always the exact same, it would go in that straight line right there. which I kind of drew. But that's not the case. What happens is we have a band that looks somewhat like this. If you notice, this green band tends more towards the neutron side, and that's exactly what we saw on this last slide. I'll go back real quick. That's what we saw here, that as we go higher, as we get more protons, as we increase the atomic number, we need more neutrons in order to keep that nucleus intact. So what this band tells me is, if it is within this band of stability, it's going to be a stable nucleus. And a stable nucleus is not going to rip apart, it's not going to decay, it's what we want. It has the perfect number, the ratio of protons to neutrons. But if it is anywhere outside this, and I'll change colors here, so if it's anywhere outside this band, this is going to be an unstable nucleus. So again, this is just a way that we can visualize this and figure out, is it stable or is it unstable? Okay, so let's talk about the three types of radioactivity. We have alpha, beta, and gamma radioactivity. And again, radioactivity is simply the nucleus breaking down, parts being broken off an atom. And usually, sometimes even forming another type of atom. So let's start with our alpha radioactivity. This is an alpha particle, and what you have here is the red ones are protons, so we'll go plus charge for this, and the white ones are neutrons, so these have zero charge. And if you're thinking 2 protons and 2 neutrons, alpha particles are actually a helium atom. And what do we know about a helium atom? They have an atomic mass of 4. Why? Because 2 protons and 2 neutrons equals 4, and they have the atomic number of 2, which would be 2 protons. So what do we know about this? We know that alpha particles have the weakest amount of energy. You see a piece of paper here, and alpha particles can't even penetrate a piece of paper. So again, make sure you know what their charge is. Alpha particles are also a positive charge particle. And in essence, it is a helium atom, and they have the lowest amount of energy. They can't penetrate even a piece of paper. Okay, moving on, we have our beta particle. Beta, that's the Greek letter beta. And a beta particle is, in essence, it is an electron. So a lot of times you see it portrayed as this electron. Electrons have 0 mass, and they have a -1 charge. So a beta particle has a negative charge, whereas an alpha particle has a positive charge. And you see that this piece of paper isn't going to stop the beta particle, but a piece of metal will. Aluminum would, even a piece of wood, sometimes lead would stop it. But a beta particle has a little bit higher energy than alpha, which, as you can see, it's going through that paper. So make sure you know that it's a -1 charge. Make sure you know a beta particle is in essence an electron, and it has a higher amount of energy. So we'll go with our last one here, and this is a gamma particle. Gamma particles have no mass. And they're really just energy. So they're not mass, they're just a bit of energy. If you think to your different waves back in the day, so if you start with the largest waves, microwaves, and we get a little bit smaller visible light waves, and then we start getting real small in here, we know this side over here as gamma waves, right? And gamma waves has the highest amount of energy. They're very hard to stop. Paper's not going to stop it. Metal's not going to stop it. You even have a nice piece of lead right here. Maybe concrete would stop it, right? And after all 3 of these things in front of us, this is the type of energy given off by a nuclear bomb. So this is why we in the 60s, bomb shelters were made, right, with a lot of concrete, hoping that this energy would not be able to get in to a bomb shelter. Okay, so finishing up, let's talk about radioactive decay, and let's do a few problems. You're going to see these in class where you have, in essence, we call these nuclear equations. So let's start out, and I'm going to make one up here. Let's take uranium, and let's take uranium 92 is the atomic number, and 238 is the atomic mass for uranium. And this is going to be an example of alpha decay, or an alpha particle, DCAY. Okay, so this is going to be similar to an equation in math. It's a chemical equation, which we know this is the yield sign, right? Very important. Okay, so we know alpha decay is actually a helium atom. Remember, 4 is the atomic mass, 2 is the atomic number. So this will be given to you in the problem, the reactant side, and then this part of the product side. We need to figure out what goes right here. So a few things that we need to do. We need to make sure that these numbers all add up together. So if we have a helium atom, a helium nucleus taken away from uranium, think about what's happening. We have 2 protons taken away, so 92 minus 2 is going to be 90. And then on our top we have 238, and we have 4 of the mass of the protons and neutrons taken away. 238 minus 4 is 234. Well, think about this. This is the atomic number and this is atomic mass. No longer do we have uranium, but come over to your periodic table. What is it that has 90 as the atomic number? It is now thorium. So that's what we're doing on an alpha decay problem. Let's look at another problem. Let's look at beta decay. So here's an example. We can have cesium. Cesium has an atomic number of 55, and it's got an atomic mass of 137. Here's our reaction, and this is going to be beta decay problem. So a beta decay problem, we know beta decay has an electron that's taken from cesium, so that would look something like this, right? So it's got a charge of -1, it's got a mass of nothing. So we need to figure out what is going there, right? So this is important because it's a little bit backwards. If we're taking an electron away from cesium, that actually means we're adding a proton. So instead of 55, this now is going to be 56, and 137 and 0 don't change anything, so this is 137, but now this is no longer cesium. So what's atomic number 56? We're going to come up here and we see that this is now barium. And one way I can check this all is, does this add up? Does the law of conservation of mass come into effect? 56 plus a -1 is 55, and 137 and 0 is 137. So we're square across it all. That's just a few of the problems we'll have an example of in this unit.